Hello. We're going to talk today about the remainder theorem. We'll eventually get there. So what I can do is I can connect the remainder of a polynomial division problem with the result when we substitute that value in and evaluate. And so the first thing we're going to do is we're actually just going to evaluate, kind of review, but f of 2, what this really means is that x equals 2, so I'm going to substitute it in. 2 squared plus 8 times 2 minus 7. 2 squared is 4. 4 plus 16 minus 7. That's 20. 20 minus 7 is 13. So pretty quickly, we can evaluate these. I really love the use of parentheses as I'm substituting into any expression the values. So negative 1 cubed, that's 3 negatives, so that should be negative 1. Negative 1 squared is positive 1. Positive 1 times negative 2 is negative 2. Negative 5 plus 6. And so my evaluation of this would be negative 2. Finally, I have x cubed plus 4x minus 5. Again, substitute each one into parentheses, plus 4 times 5 minus 5. 5 cubed is 125. It's okay that it's a fairly large number. That doesn't bother us at all, hopefully. 4 times 5 is 20. 20 minus 5, so I have 145 minus 5 is 140. So a nice, gentle way to get us involved in the problems. We've seen these types of problems before. And now we're going to get into the connection piece. So the classwork objective for this is I can connect the remainder of the polynomial division problem to the result when we substitute a value and evaluate. So you probably are wondering what that means. So we'll go through a couple examples and see if you can't put it together. And what it says here is divide. So divide by x minus 2, so I'll put x minus 2. I'll use long division for this. You can use reverse tabular method, but I prefer long division just because of the fact that if I have a remainder, I can work with it a little bit easier. And so I look at what number do I multiply x by to get x squared? Well, that's x. X times x is x squared minus 2x. I change the signs because I'm subtracting it. And I see that this would be x squared minus x squared is 0. 8 plus 2 is 10x minus 7. And so I get 10x minus 20. Reverse the signage because we're subtracting, so this becomes plus 20, which leaves me with 13. Since I'm in the mode of dividing, maybe I'll do all three of them all at once, and then maybe we'll come back and make a connection. So the next one is x plus 1. And I have x cubed minus 2x squared plus 5x plus 6. What do I multiply x by? The x cubed, x squared, so x squared times x is x cubed plus x squared. I need to change the signs. I always circle them. Once I've done that, it's my indication that I have actually done what I was supposed to do. So negative 3x squared plus 5x. So I'll do minus 3x. And negative 3 times x is negative 3x squared. Negative 3 times 1 is negative 3x. Go back through, change the signs. And I have 8x plus 6. So I need to multiply by 8 plus 8. Go through this, and I'll get a remainder of negative 2. Cool. Next problem. Consider the polynomial function h of x, so I'll get h of x from above, x minus 5 goes into x cubed. Now I'm going to remind you that you need to add in the missing x terms. That's probably the #1 mistake kids make. They forget to do that. They just get in such a rush. They're not thinking about placeholders, and we definitely need placeholders with division. So make sure you do that. It's super important. We're almost done bringing that last term down. Plus 29. 29x minus 5 is -145. Change the signs. Again, if you don't have different colors, circling is your indicator, and I'll realize that this is 140. Now you notice I didn't rewrite any of these as quotients with remainders, because as we look back, our goal was to connect the remainder of the polynomial division problem to the result when we substitute the value and evaluate it. Well, when I looked at this, and you might be wondering what's the connection between the factor and the value within the function, just as a reminder, so x minus 2 equals 0, and so this is x equals 2, and that's where I got this 2 from. And so what I'll notice is if I look back at the very, very beginning, it wasn't done arbitrarily, but this was 13, and my remainder is 13. So if I'm going to compare the two, I would have to say that the remainder of the division problem is the same as f of 2 evaluated. Well, let's see if that trend continues. If I look back up, I see this is -2, and I look at my remainder. The remainder of the division problem is the same as, not f, g of -1 evaluated. Well, now we've had 2 in a row. It'd be really awesome if we could get a third result that same way. And in truth, we do, because when I evaluated h of 5, although it was a fairly large number, it was 140, well, so was my remainder. And so my conclusion might be the remainder is equal to the evaluated expression. The remainder is equal to the evaluated value in the function. You might be wondering, why is this a nice result? Well, if we're trying to figure out if something's a factor, remember, if it's a factor, factors have remainders of 0. And so ultimately we can use this, and you'll see some problems in the classwork that does. And the next part says evaluate this, really just to check our hypothesis. So we'll just check it one last time. F of x was x squared plus 8x minus 7. And so if I evaluate f of, it says when x is 1, and again, the connection between the root and the factor is really an important one. f of 1, so 1 squared plus 8 times 1 minus 7. That's 1 plus 8 minus 7, which is 2. The next thing I'm supposed to do is check, now that I've gone the other direction, x minus 1 into x squared plus 8x minus 7. So I need an x times x squared. X times 1 is negative x. I'm subtracting, so now I get 9x minus 7 plus 9x minus 9. Again, I circle whenever I've switched the sign so that I know I've done it. It's sort of like a check for myself, and what I see is that my two remainders act the same. And so what we do is we have this sort of generic general proof, and what I would notice is that I can rewrite my polynomial function as an expression of the quotient times the divisor. We've covered this all along, and occasionally there's a remainder. Now if we do this in a generic space, the quotient, we'll just call it a function q of x. The divisor we know is x minus a, and the remainder we'll just call r. Well, what they want to know is when x equals that value, so x equals a, what happens? Well, if I substitute in, I get p of a equals q of a minus a plus the remainder. Well, something nice occurs right here. What I'll notice is that this a minus a is 0. So p of a equals q of a. Remember, this is not multiplication but function notation. But this is times 0, which wipes that out. And so p of a is equal to my remainder, which is exactly what we've been finding out all along. And you can sort of check this. And so here's the result. When I divided by x minus 1, this is the quotient. This is my q of x. This was the factor, and there's my plus 1. And so the question really belies what happens when I substitute 1 into this. So f of 1 equals, well, 1 plus 9, 1 minus 1 plus 2. 10 times 0 plus 2 equals 2. So f of 1 equals 2, which as a reminder is equal to your remainder. So you might want to pause the video and summarize it. I have the remainder theorem that you can write down at the bottom of my page. So let me put this up there. And now that's in full screen so that you can see it. That's the more formal way to write the remainder theorem. If you've divided a polynomial by the expression x minus a. Thank you.